Hello, my dear. Welcome back. Today we're taking a second step in building our understanding of neural networks. I'm Aliana Moran, sometimes known as Dr. AJ. This vid is one of a series that's built to accompany my book in progress, Statistical Mechanics, Neural Networks, and Artificial Intelligence. Let's briefly overview what we're going to discuss today. The focus is the transfer function, but to get there, we need to decompose the architecture of a single node and get a good understanding of how that works. Then we'll put the transfer function into context. There are several different kinds of transfer functions. We'll touch on all and give most of our attention to the classic sigmoid transfer function. Then we'll take a look at its derivative, and after that, the implications of what the derivative of the transfer function means when we're working with neural networks. Let's get started with a quick review of where we left off last time in the previous vid on notation for neural networks. In our previous vid, we discussed not only things like the nodes in a different neural network in the various layers, but also connection weights and bias weights. For the example that we're going to use, we're going to pick the rightmost node on the hidden layer that you can see in the network that's shown on the left. This discussion is using that example of a hidden node. The very same arguments apply to nodes in the output layer. Yep, those are roosters in the background. Not even going into that story right now. So regardless of roosters, let's just keep at it because they're going to keep at it. Getting into this transfer function business for a single node, we're taking a look at a hidden node. Same operations go on exactly for an output node. The inputs to either kind of these nodes are going to be the sum of the weighted outputs of each node in the preceding layer. So in this particular case, we have 5 different inputs because we're talking about a neural network with 5 nodes in the input layer. When we're communicating from the hidden to the output layer, this particular MLP has got 4 hidden nodes in the hidden layer, so we'd have 4 inputs going into a single node in the output layer. When we were looking at the inputs to the hidden node, you saw that I had 2 different colors of arrows. I had red and gray. So the red ones were corresponding to on nodes in the input layer, and the gray to off nodes, so they really weren't giving any input because you multiply the weight by 0 and you get 0. You can see that I've got 1 on, 1 off, 1 on, 1 off, and 1 on in the input layer, and the output layer has the middle one on. The other 2 are off. So I'm showing the on ones in the input and the output layers as a bright orange. In the hidden layer, I'm showing that there are 3 red nodes. Those are like sort of on. They don't have to be like a total value of 1. They can be, 0.7 is good, 0.8, 0.9. Let's go through the math for this next little step. We're looking at the input into hidden node J, where J equals 3, because that's the last hidden node in that hidden layer set. We're counting once again Python style. J equals 0 up through 3. The sum runs over all the nodes in the input layer. So we're running over I equals 0 up through I equals I, capital I, where that capital I equals 4, and that's a total of 5 counts. The weights in this case are running over Wi sub j, where j is 3 throughout. You'll notice that the summation sign is over I. J is constant, so j refers to that last hidden node that we're using as our example. The I part runs from 0 up through 4, so we have 5 different weights. The output of that node, sometimes called the activation of the node, is the transfer function applied to that total set of inputs, that is, the sum of the weighted inputs into that node. So let's consider our various options for the different possibilities on a transfer function. There are 2 basic types. One is the sigmoid, which is sort of an S-shaped, an elongated S-shaped, and the other is any other kind. It could be sort of truncated or linear or some approximation thereof. There's quite a variety around there. We're going to focus on the simplest of the sigmoid transfer functions. Before we get into the graph, let's have a look at some of the mathematical particulars that make this kind of transfer function so appealing and make it workable. In other words, it makes the backpropagation algorithm work. The first key point, and this is going to be true for all transfer functions, is that it is continuous. A continuous function is one that has an output value for every input value that you would put into it. Not only that, it never takes any weird, sharp jumps. When you look at the transfer functions over the next few graphs, you'll see that they really don't tend to split apart into several different lines. They're always connected. Next, and this is so important, the sigmoid transfer function is smoothly differentiable. That means its first derivative exists at every point along its existence. We really need this for the backpropagation algorithm to work. Third, and this is one of the big reasons that we use a transfer function, is that it's bounded. That means the output of the transfer function is going to be between two numbers. Let's just have a quick look at the sigmoid transfer function to see what this means. We can see that if x goes to a large negative, and here minus 3 is actually kind of large, the transfer function never goes below 0. And if x becomes large positive, again, going towards plus 3, for this case kind of large, the transfer function isn't going above 1. The transfer function is bounded between 0 and 1. Our fourth key point about the transfer function is that it's monotonically increasing. That means that if we look at it from left to right, it's always going up. It might go up just an itsy-bitsy tiny little bit, but it's going up, never down. Our fifth and last point about the transfer function is that the derivative is maximal when the inputs are 0. That means you get the greatest rate of change, or biggest slope in it, when you've got about 0 inputs. This is going to give us a lot of value when we try to change connection weights, so it's a very practical point. Now that we've made some comments about the math, let's get into the math itself. We see that the transfer function, we're calling it f, is a function applied to the input variable x, where x stands for the sum of the weighted inputs into the neural node. This classic, sometimes called logistic transfer function, is 1 over the sum of 1 plus the exponent of the negative of a coefficient called alpha times x. Just looking at the transfer function equation, it might be a little difficult to figure out how it shows up as the final graph. So I've got the elements broken down in this table. The first column has our input into the transfer function. We see that the central point, 0, is the first one, and then we have 2 points to the right at 1 and 3, which is the farthest right that we have on the graph. And then we have minus 1 and minus 3, which take us to the left-hand side of the graph. The second column is e of minus x. The third column is 1 plus e of minus x. And the fourth column, the final one, is our actual transfer function output value. Let's check out some specific numbers for the transfer function. When the input is 0, we take the exponent of 0 and get 1. Then we take 1 plus that and get 2, and then 1 over that and get 1/2. Here's an important little technical side note. When you're training your neural network and you're just beginning the training, it's very common for either a hidden node or an output node, or both, to have output values that are about 1/2. And that's because the weights into them have not been trained to give you either a strongly positive or strongly close to 0 output. We'll pick up on this point again later when we start looking at how the backpropagation algorithm actually works, and we take a look at some examples. When the input to the transfer function is a positive number, then the exponent of the negative of that positive number is a fraction. It's going to be less than 1. And then when we add 1 to it, we get a number that is over 1, but still kind of small. In fact, the bigger that x is, that's the smaller that 1 plus e to the minus x is going to be. It'll be very close to 1. Then, when we take 1 over that number, we get a number that is a fraction, but it can get kind of close to 1. In contrast, when we have negative inputs, such as -1 or -3, and we take the exponent of the negative of that negative number, we're taking the exponent of a positive number, so we get kind of large results. We add 1, and if our original number was a small negative number, such as -1, then adding 1 will make a significant difference. Take 1 over that number, and you get a fraction that's less than 0.5, but still kind of significant. On the other hand, if our input is kind of a large negative number, like -3, and we take the exponent of the negative of that and get, say, about 20, then when we add 1, it doesn't make a great deal of difference, and 1 over that is a really kind of small number. We're starting to get close to 0. Let's take a look at a couple of other transfer functions, and then we'll come back and, working with the sigmoid transfer function, we'll take the derivative and see what that looks like. The hyperbolic transfer function is very similar to the sigmoid transfer function, that is, the logistic transfer function, except that instead of going from 0 to 1 as its y range, it actually goes from -1 to 1. You can see that the slope is a bit steeper. As a non-sigmoidal transfer function option, there's the ReLU, which stands for rectified linear unit, and its logarithmic approximation. The ReLU is by now the world's most commonly used transfer function. It's common in convolutional neural networks and also in deep learning applications. However, our goal right now is to understand the transfer functions that are used in backpropagation. So for that reason, we're going to go back to the sigmoid transfer function. This figure shows the derivative of the sigmoid transfer function. You can see that the derivatives for each of the different alphas are all bell-shaped curves. The derivative for the sigmoidal transfer function is given here. You can see the equation, but I'm going to ask you to derive it for yourself as an exercise. You can see that the derivative is at a maximum when x, the inputs, are 0. This implies that it'll be easiest to change the connection weights when the inputs are close to 0. Conversely, the derivatives approach 0 the further that we get away from the place where x is 0. This has got a huge impact on backpropagation. The reason for this impact is that in every layer of weight adaptation, we use the gradient term. However, when we do the input to hidden weight adaptations, we wind up multiplying 2 gradient terms by each other. So if both of those terms are very small, then we get an extremely small value there. Imagine what would happen if we introduced a second hidden layer. Then we'd have an input to hidden layer at the very bottom that would have 3 derivatives or gradients multiplying each other. You can imagine how small that would be. This has become famously known as the vanishing gradient problem. What this means is that we can build simple neural networks easily, neural networks that have just 1, maybe 2 hidden layers. But if we try to expand beyond that, in other words, build a deep architecture using backpropagation alone, this vanishing gradient problem overwhelms the learning capability. Deep learning methods provide the solution. We'll be looking at those in future vids. Here's a screenshot of the blog post, and if you lose track of this, it'll be easy to find just by Googling my name and the keyword transfer function. The chapter on transfer functions still needs a lot of revision, so it's not available right now, but as soon as it is, I'll make a link to it from my book page. Once again, thank you for joining me. This is Dr. AJ, and it's been such a pleasure to have you with me today. If you've enjoyed this and want to be informed of future vids, please do the following standard YouTube things. First, hit the like button, that thumbs up right beneath the vid. Second, if you haven't already, subscribe to my YouTube channel. Haven't you heard that phrase before? And thirdly, if you want to be informed, hit that notifications bell. Feel free to comment. Please be as kind and courteous as you would if you were actually talking to someone. but this is a great place in which to have a forum and to share ideas. Thank you again. Till soon.